30. Okay, that's what this tree looks like right now. So if you try to insert this value into this tree, what happens is it obviously goes here and there's no space. What you will do is you will allocate a new page. And you do a split of these entries. Those entries that are already in this page with this new entry. So what happens is, if we do a 2-3 split in this case, which essentially is B and B plus 1 split, B is the order of the tree, half the capacity of a node. You end up with this. You follow me? And then what you will do is you update the pointers properly. So this will link here and this will link here. And then you make an entry for this. In this particular example, since it's leaf level you do what? Set. You copy up the key value. Which key value you copy up? Well, the smallest third key value from the second node, the node you have just created, because you want to index this node. So what happens is you have a 5 and pointer back to this page. That's the entry you try to, so you copy out. You don't delete this from here. So actually you cannot delete this from here. Why? Because every entry in the leaf level corresponds to an actual record in your data file. So you have to have a representative for each record in the leaf level. So you cannot remove this key value from the leaf level. Okay, so you try to place that into this node, what happens? You do not have space, you have to split again. And in this case, you do the split. So what happens is you're going to allocate a new node. Let me just erase this pointer for now. And this 2 nodes down still be here. The 2 additional leaf nodes. And 4 entries here. You split. You do a 2-3 split, which means 3 entries down here, 2 entries stay here. Among these guys, 3 entry coming over here will be 17, 24, and 30, along with their pointers. So this will still point here, this will still point here. And 17 point to here, right? So now since you move this entry over, this pointer will come here. Okay? And you remove them from here. You have to make space for this. So move 13 come over here, and this pointer will be redirected. Now you have the space needed, right? To place 5 here, and the pointer simply come here. Do all of you follow me? What's going on so far? The next thing is you want to make an entry above, right? Because you have a new node in this level, you have to have an entry above to index this. So what you do is you copy out the smallest key value from the second entry, from the second node, which is 17, and make a pointer back to it. But since it is index level, there's a special thing about index node, which is the leftmost pointer. For that reason, you do not copy up, rather you push up the key value of the first entry after the split. This is gone, and this pointer becomes your leftmost pointer. Then you have an additional space in the end, and this kind of makes it clear. This narrows down a little bit. That's your leftmost pointer. You follow me? And then this goes to you have no node in the level above, so you have to create a new root node in this case to accommodate this entry. So you will just produce a node for it. which has this many entries, 4 entries, and add the leftmost pointer to the left side node from this level. Then you are done. Okay? You follow me? So that's the resulting tree. Okay, that's the insertion procedure. Okay. Next, we're going to talk about deletion. So before I talk about deletion, let me talk about how you're going to implement this in your project 3. So, a major challenge in implementing this is, you see, when we come down from the root to the leaf level, when we descend down this tree, what you do is you use pin page, right? First of all, you need to know where the root node is. So there is page ID for root. This is a system-wide parameter. The database system will store this value in a what we call metadata table. So it's a fixed location in your database, so database knows where to look up this information. And that's all you need to know about this index from the database point of view. Because once I know the page ID for the root, I load it, this page, I pin it. Right? By loading, I mean pin it. Pin page with this page ID. It will bring this page to the buffer. And once in the buffer, you can compare the values. And then find out the page ID to follow to the next level. You go down, 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 all the way to the leaf level, right? The challenge is when you have this kind of split happening, which goes back to the level above. The tray, if you check this, the tray allows you to go down, but no easy way to go up. Right? No easy way to go up. So how am I supposed to implement that in project 3? When you realize there's a split at the leaf level, when you try to go up, by the time you realize you need to do this, it's already too late. You no longer have the information about who is your parent node in the level above. And this goes back all the way to the root level, right? So the way you're going to implement this is to use recursion. So let me just briefly talk about that. So suppose you are here. You stand here. Sorry, it was split tree. Okay. Anyway, fine. So let me use this example. So suppose you stand here. Let's say we try to insert another value called 9. This. What happens is you call the insertion function on this node. So there's an insertion function defined for each node of the tree. And what you do is you find the right pointer to follow to the level below, and you call the insertion function on the node below you. For example, for 9, I should call insertion function on this node. But so let's say this is the node 1, and I label this at node 2. What happens is when you're at node 1, you call insert. And inside this implementation, what's going on is you basically wait for node 2.insert, where node 2 is the right node to follow to the level below, depending on your current key value you try to insert into the tree. You follow me? And if this returns nothing, what do you do? Well, you return nothing at all. You return immediately. Because what that tells you is, you view this as a black box. What that tells you is this key value, this entry, of course you call the insert with this object. If this returns nothing, what that tells you is this entry has been inserted in the subtree rooted at this node. And it doesn't go back up to this level. So you don't have to worry about inserting an entry come from the level below. You're done. So whoever call you, then there's somebody else, if it's a recurrent, someone else is calling this procedure, right? They are waiting for you to return, then they can return immediately once you return. The other case is what? Otherwise, it will return something. What does it return? It will return some key value k prime, and a point on page ID, entry, right? Essentially, it's 5. We just put it up. Then what do? You grab this, try to place into your current node. If there's space, you're done, you return nothing. If not, you split, you will return an entry to the level above, whoever is calling you, the insertion function on this current. So that's the recursion implementation that you will do. You follow me? If you understand what I'm talking about here, you should be able to do your project tree. That's the core function for your project tree. Of course, in each of these steps, whenever you need a page, remember you need to call pin page from the buffer manager to get the page, rather than trying to get the page yourself on disk. That will mess up the whole thing. Which means you should have a deep understanding of buffer manager that you have just implemented. Okay. Now let's talk about deletion. So there's some illustration, but I think I've gone through this example already on the chalkboard, so I'm going to skip this. So now let's talk about deletion. So the major challenge for deletion is because we want to enforce this concept called order. By the way, there's a pseudocode of this algorithm I just mentioned from the textbook. So you can refer to that pseudocode from textbook to understand, to try to go back and re-understand what I just said. Now, for deletion, the major challenge is to ensure that a given page is not going to be underutilized. By underutilized, I mean the number of entries in a page is less than b, less than order of the tree, less than half of the capacity from a given page. When that happens, we see that tree is underutilized. And the reason we don't want a tree to be underutilized is because if you follow the analysis I did last lecture, the query cost for a B-plus tree is directly related to the height of the tree. And the height of the tree is roughly this number, which is where n is what? N is number of pages in the leaf level. N is number of pages in the leaf level, right? F is what? F is the fan-out. So if a page is underutilized, your fan-out will be too small. Right? Because fan-out essentially is the number of entries in a page plus 1. So if a node is underutilized, your fan-out is going to be small, which means the height of the tree will be bigger. This value will be bigger, which means the query cost for B plus will be higher. Essentially, that's why you don't want any page to be underutilized. So, with that constraint in mind, when you do deletion, there were challenges. The first step in deletion is the same as insertion, which is to find the node that the current search key value should reside in. You try to find the node. If you go all the way to the leaf level and there's no leaf level node containing this search key value, well, good news, you don't have to do anything. It doesn't even exist. So you don't have to do anything about deletion. If it does exist in a leaf level node, what do? Well, you remove this entry from that leaf level node, obviously. But you are not done yet. Why? Because you need to ensure the node is not underutilized. Right? So when will the underutilization ratio, when will the underutilized situation take place? Victor?
Sorry, before that, why have we returned some sort of error? It seems like if we're trying to delete something that's not there, it's probably...
You can return some, yes, this is up to you to decide. Typically, of course, the interface will return a message that will indicate this value doesn't exist in the database. Okay? Okay, let me continue. So, if the current node you find, if I follow the notation in the slide, if the node L in the leaf level has more than B entries, then you are done, because by deleting one entry, you guarantee that you still have at least B entries left. More than B entries means -1 implies it's still greater or equal than B. It might not be greater than B anymore, but it's greater than or equal to B. So this is the case 1. Case 2, it has exactly B entries. Now if you -1, what that imply? Now it's strictly less than B, which is underutilized. This is the case you need to deal with. You follow me? So how do you deal with this? Well, if you look at the insertion procedure, a very natural solution is to do what? Well, you merge. Yes, precisely. You merge this node with a sibling node from the same level, of course, so that after the merging operation, they reside in one node, and underutilization is gone. Okay, that's one option. But merging is expensive, right? Because merging means that you are changing the structure of the tree. It's expensive, so we want to try. We try to avoid doing a merging operation if possible. So what is another possible approach? Well, you can do redistribution of the entries between the current node and the sibling node. It's kind of like, okay, Eric has $200, and I currently have $100. So the requirement is each of us should have at least $100. So we're good. But then Charlie came to me and said, Feifei, I want $1 from you. I said, no. And he said, well, you have to give me. And then he used some kind of, I don't know, black box operation. Then I gave him $10 in the end. Okay. So now what happened is I have $90 left. And Charlie is auto picture. And Eric has $200. So what I want to do is I want to redistribute the entries we have, where the entries here is dollars. So if Eric just gave me $10, we are good. Each of us will have at least $100 again, without changing the status quo. Meaning that Eric and I are still two separate entities. Merging means somehow Eric has to agree to merge with me, become one entity. Which is obviously not an ideal situation compared to, well, it depends, right? From Eric's point of view, whether you want to have $290 or $190. Maybe after merging, he controls everything we do, right? So that's a simple example to illustrate what's going on here, right? So, but merging is not always possible, right? If Eric only has $100, I have $100. Now I left with $90. Then if I try, redistribution is not always possible. So if I try to redistribute money from Eric to me, no matter how you do this, it's not gonna be okay. And that's a simple paging hole argument. Right? That's a simple paging hole argument. So let's look at how exactly we do redistribution. That's the basic idea, right? How you do redistribution or merging. So you always try to do redistribution first, if possible. If redistribution fails, you do merging. But when you do merging, the tricky thing is you have to delete an entry from level above. Because it used to be you have two nodes to index in this level for the level above. But after merging, you have only one node left for the level above to index. So you have to remove one entry from level above, which potentially will create a problem for you which means you are doing a deletion in the level above, which may lead to the node in the level above to be underutilized. In other words, this deletion can be trickle back all the way up to the root. Okay, that's precisely the expensive part of a deletion. Okay, let's see a concrete example. So this is a tree that we have just produced after inserting this entry 8 and record ID for that value 8. So this is the tree. Now we want to delete 19 and 20. How do you delete 19? You come down to the tree. This is the L, this node we refer to. remove that. That's easy, right? Because the node is not underutilized. Why? Because the order of the node is what? In this case, is 2. B equal to 2 because the maximum capacity is 4. Half of it is 2. After I remove 19, I still have 2 entries left, so it is not underutilized. Okay, so I'm okay. Now, if I have yet another deletion coming in, which is to delete 20, now what happens? I'm underutilized. And you try to do redistribution. By the way, when I say redistribution with the sibling node, the sibling node has not been formally defined, right? So sibling node refers to your immediate right or left neighbors from the same level and who share with you the same parent node. Which means the sibling node of this node is only this node, but not this node, even though it is immediate to the left of this node, but they do not share the same parent. So the sibling node of this node is only this node right here. Okay? Good morning. So now imagine these 2 entries are gone. Can you do the first thing you want before you do redistribution is to check whether it is possible to do redistribution. And in this case, you can, right? Because you have more than B entries to the node in the node to your right in your sibling node. So basically, how do you check that condition, whether you can do redistribution or not? Well, you know this current node minus 1. Actually, it's not less than B. It's exactly going to be B minus 1. So if your sibling node has more than B entries, then you know redistribution is yes. Why? This is a simple pigeonhole argument. Each hole must have B elements, but you have more than, in total you have more than 2B elements. Then of course after there is a way to distribute them into 2 boxes where each has at least B entries. So what is the situation you cannot do redistribution? When the sibling node has exactly just B entries, then nothing you can do. Right? B minus 1 and B. You only have 2B minus 1 entries and try to distribute them into 2 boxes. There's no way you can ensure each of them has at least B entries. Okay? So in this case I can, because there's 3 entries, in total I have 4 entries, so I can do a 2 and 2 redistribution. By that, what happens is 22 will come here, 24 will move over here. But you are not done yet, because by moving 24 over, what it means is you need to update the entry in the level above. So that 24 should be gone and replaced by what? The new smallest entry from this node, which is 27. So that's what happens. Okay, so that's the redistribution taking place. Yeah, Victor.
So when we redistribute, is there any just like take one or take like half from here, half from there?
Yeah, so there is no kind of like strict rule what you need to do, but generally you want to do a balanced redistribution, half and half, roughly speaking.
And then do you want to try to balance, like if you have a left and right page, do you want to try to balance all 3 together maybe, or just?
No, if you have both a left sibling and right sibling, what you will do is look at which sibling node has more interest, and you do redistribution with that. The reason is, if you have a left sibling and right sibling has more interest than the left sibling, why you want to do redistribution with right sibling? Because that reduces the chance of an insertion split to the right sibling node down the road. Because it has a higher chance to be full by future insertions than the left sibling node. Do you follow me? It's kind of like if I want to borrow $10, okay, should I borrow from you or should I borrow from Bill Gates? Which one has a better chance? Well, if I don't know both of you, right? Of course, I know you. I don't know. I actually met Bill Gates once, so I kind of know him. But $10 for him is nothing, right? So that's my argument, right? So you want to redistribute with the one with more interest. Now if we do further deletion, let's say we want to delete 24 next. So delete 24, easy. This is gone. What happens now? Can you do redistribution? You cannot, because the only sibling node is this one. You only have B entries. You have B minus 1 entries. In total, you have less than 2B entries. There's no way you can do redistribution. So what do? You merge. You merge these two nodes together. That gives you 22, 27, 29. And what? You need to delete the entry in the level above that index this node that being merged. Which means you need to delete what? This 27 and this pointer from the level above. Which means the level above becomes this, right? Becomes 30. With only one entry in it. So this node now becomes underutilized. Right? So I have to do something about it. So what do? In this case, you try to do redistribution with your sibling node. Can you? You cannot, because your sibling node only has 2 entries. You have 1 entry. Again, you cannot do redistribution. So what do? You merge again. So you merge this node 30 with only entry 30 with this node with 5 and 13. Here comes the tricky part. For leaf level merging, you simply merge the 2 nodes. You're done. For index level merging, you need to remember what you did in insertion in order to carry out the merging properly. In insertion, when you do a split, what happens? You push an entry up. So when you merge, you need to pull that guy back down. Right? It's exactly the inverse operation of a split. Right? So for split, you push an entry up. So that entry should be at this level when you do merging. So when you merge, you pull that entry back down. So what happens is when you merge these entries, this node 30 with this node 5 and 13 on the left, you pull that entry 17 down from the level above, which gives you the new root node of this. You follow me? And this pointer for this entry 17 is actually the leftmost pointer in that node, which, if you recall, was the pointer associated with this value 17 in the first place, before it was being pushed up to the level above. So everything is in good order again. You follow me? Yes? Okay. So let me demonstrate yet another case where a deletion will result in a non-leaf level redistribution. So because currently in this current example, what we see is a non-leaf merging example, right? But we haven't seen a non-leaf, in other words, index level redistribution. An index level redistribution is also trickier than leaf level redistribution. The reason, once again, is because the way you do insertion and split. When you do insertion and split at non-leaf level, what happens is you push an entry up to the level above. So when you do redistribution at the non-leaf level, you should involve not only the entries from the 2 nodes in concern, but also what? That entry in between of them in the level above. Because that entry was from these 2 nodes as the result of the split. So when you do redistribution, you need to involve that entry from level above as well. So let's look at a concrete example. Suppose that's where I am. So let's say I delete some entry here, I merge 2 nodes, I delete entry here, I end up with this node. But in this particular case, I do have enough entries to redistribute from my sibling node. So what happens is, who's gonna come here? Suppose I'm gonna do a 2-3 split. So I have more entries here than over there. So who should come here? Well, the first guy to come here is 22. So you do redistribution like that. You involve the two nodes in concern, as well as the entry in between the two nodes from the level above. Because this entry was originally from this node in the first place. Okay? So you redistribute 22 come down. When you move down 22, you move up 20. So you can just imagine there's a chain going like this. And then you push one by one. Kind of like that. That's it. So 22 comes down, 20 go up. That will be fine if you do a 3-2 split. If you do a 2-3 split, you keep pushing. You push 17 up, and 20 will be pushed down. So the end of the day, it looks like this. Okay? That covers, I believe, all the cases. That covers, I believe, all the cases. Okay? So that's the deletion of V+3. As you see, the deletion is slightly more complicated than the insertion. The good news is you do not have to implement a deletion as it is in your product 3. You still have to do deletion, but what you do is you simply remove the entry without worrying about underutilization ratios. So if a node is underutilized after deletion, let it be. So that's trivial, right? You just find it and remove it. So product 3, we do not require you to do redistribution and merging for a deletion. Do you follow me? Yes, question? What if that page is empty? I believe in our test cases, we do not produce a situation like that for you.
So in the test cases, like our insertion should work properly for this deletion test case to pass, or?
Well, your deletion should work as well, because you know, if you don't do anything about deletion, your code still is wrong. Right? At least you need to find where it is and remove from the tree.
No, for example, say if I do not implement the insert part properly, so is the test case dependent on the insert?
Of course, yes, it is dependent. I mean, what you are saying is, if I don't do anything right about insertion, can I still get credit for deletion, right? Actually, it's an excellent question, right? So, well, we will look at your code and give you credit, yes, we will. But the task cases, I believe, are dependent on the insertion, because they always do some insertion first. You have to do the insertion to begin with, right? If you are empty tree, how can you, what to delete from, right? So it does depend on your insertion code to work properly in order to reach the part to test the easy part of your code. Unfortunately, that's the case. Right? But we will, if you think you have implemented deletion right, you can add a README file in your submission and say, oh, my insertion doesn't work, but my deletion actually works. Go check it out. So the TAs will read your code. And if I were the TA, I would take your word for it, give you one. Deletion is like, go down the tree, find it, and remove it, right? It's not that hard. Okay? However, that said, right, if you don't understand how buffer manager works, you may not even get that deletion work properly. Because you still have to pin page, still have to understand how pin page, dirty bit, and all that stuff works. Because when you remove an entry from a page, that page becomes dirty. You need to remember to set the dirty bit and all that stuff. And don't try to write the page back to DC itself, but let buffer manager handle it. You still have to have those basic concepts in mind in order to get it right.
I think I believe somebody hit a page and to mark it dirty, but if it was not written right, but if it was not updated.
What if?
So the page is deleted.
Yeah, that I get it. What's the?
Why do you mark it dirty?
Why do you mark it dirty? Well, because the deletion happens in memory, right? In buffer. You modify this copy of this page in memory. So after removing an entry from this page is updated in memory but not on disk. The copy of this page on disk still has an entry in it.
So I get how can we say that the page was updated? So like we brought it into the memory and we just deleted it. So
You delete an entry from the page. You are not deleting the page.
Yeah. Oh, wait a second.
Right? See what I'm saying? Okay. All right. Any other questions? Not, we're almost done with VPAR 3. Okay, I'm happy with that. Okay, so now, and that's it actually. Okay. There's one more thing that's not in the slides. I will just briefly mention this, which is how do you build a VPAR tree from scratch if you have a data set, right? One solution is what? You use the insertion procedure and build it from scratch. Insert one by one. And I will show you why that doesn't work well. Okay? Suppose I want to, very simple, my order is 2. Okay, so I start inserting, right? First of all, I create a root node that's empty. So my tree initially has only one root page, and I start inserting value in it. Let's say I insert 1 with RID. Next, what do? I insert 2. So this is my insertion sequence. Okay, go like that. Next, what I do? 3. It cannot be simpler than this. 1, 2, 3, 4. Count the numbers. Oh, now comes the interesting case. What do you do next? And what happens? Split, right? Okay, good split. Let's say we do a 2-3 split. And we have to make a node above. So far so good, right? Continue. 6. And 7. What happens? And do you see the pattern? If I kept doing this, not only all the leaf nodes are exactly half utilized, this node will eventually be split and only half utilized. So you will end up with a tree. Suppose I do this all the way to 1 billion. Okay? What do you end up with? You end up with a tree that all this part of your tree is exactly half utilized, except this boundary pass that you're pushing the tree, which is bad, right? Which is the worst case you can hope for. You follow me? You follow me? So how do you address this problem? That's the question, right? How do you address this problem?
Would it be easier just to sort the insert sequence and then just build it straight up?
Exactly. What Jonathan said is exactly the Berkeley procedure I'm going to introduce, which is you sort the input sequences. In this case, I don't even have to do sorting. They come in order. But in general, you should sort them. Why you need to sort them? Because data entries need to be sorted. Then you build the pages from what? Bottom up, level by level. That's precisely the way we introduced VPAR to you in the first place, the static data structure. Why that helps? The reason is when you do that, you as the program, suppose you are the VPAR building program, you can control the utilization ratio of each page. You can argue, okay, since you have sorted, okay, I want to have 75% utilization ratio. So this 3 goes to a page. This 3 goes to a page. So on and so forth. You can even enforce 100% utilization ratio if you want. And then level by level. And that's what we mean by spark loading procedure. The difference is huge. We have a data set currently we are trying to index. That's about, how many entries do you have? We have this many entries in our database we try to index. If we do insertion one by one, it will take a few days to finish, or more than that. If we do bulk loading, much more efficient. Okay, much more. In fact, let me show you. Oh, you cannot see. So see, we are looking for bulk loading of a particular tree. Bulk loading of a particular tree. That's precisely what I'm talking about. Okay, now let's look at the next. I will use another, so I decided not to talk about the homework solution today because I want to give you some time to review it. So what I will do is I will talk about the homework solution on Tuesday, right before the quiz. And then after that, we will execute the quiz right after that. So what you want to do is you want to review the homework solution from now till Tuesday. Question here, then there, and then here. Yes.
In the bulk loading case, it will work, but if we have a one-by-one insertion, then it's gonna be the same case.
Yeah, so bulk loading only works if you have your data already on disk, which typically is the case. Then after that, you will have dynamic insertion coming in later on. Then, of course, for those, you just handle them one by one. But typically, you handle them in a batch. You don't handle them one by one. You buffer that, handle insertion in a batch, and deleting a batch. Yeah, question?
Why don't we insert the B tree randomly?
What do you mean randomly? Well, randomly helps, but still, it will be still much more expensive than bulk loading. It's the same thing. It may help the utilization. If you do random insertion, this paper I mentioned to you last time shows you, eventually it converts to 67% utilization ratio, always. So it helps to a certain degree, but doesn't. And that's only the utilization point of view. And the number of split and all that you have to do is way more than what you have to do for bulk loading. You have no split here if you do bulk loading. So utilization ratio is just one factor.
Is there a way to merge two trees?
Is there a way to merge two trees?
Like do a bulk insert into an already existing tree?
So you have one tree, you want to insert another tree? Well, there's not an easy way to do that. I mean, it really depends on the tree structure itself, right? If you after merging, you have to do a split, you have to do a split. Not, you see what I'm saying?
So in practice, when you create a new database, like new schema, then we should like load all the data and then we should create the index.
Totally.
And
You
we should not do
You don't want to create a schema, empty schema, and create index, then load your data. Because that basically is like inserting data one by one. You want to load your data in, then tell the system build index, and the system will automatically choose the bulk loading method in that case.
So now if I'm starting creating a new application, then I should initially wait for like a couple of days to get my data is coming from some source.
Well, what happens is initially your data is small. You allocate a big enough buffer, everything in cache, in memory. IO doesn't matter. When the data grows so big that your memory cannot hold anymore, this is the time on that particular date at midnight, called bulk loading. Make sense?
Yeah.
Before that, just allocate a big enough cache, a buffer essentially. A cache I mean buffer. Then your data is cached in the memory all the time. Index is irrelevant because the whole point of indexing is to reduce your IO cost. Good question though. Yes.
So typically in systems, when we build indexes, would that usually be in the background? And would that just be at like some?
Well, that's related to my answer to his question, which is you want to do it on a production database. You have transaction and data coming in actively, either insertion or update or deletion, things like that. You don't want to have an index construction process going on at the same time of that. So typically what you do is, if you want to do a bulk loading of your index, you do that at midnight when your workload is at the minimum.
But there's still going to be some updates potentially.
Well, then that's not bulk loading. That's like one insertion at a time. But typically, like in my answer to earlier question, you don't do one insertion or one deletion at a time. Rather, you batch a few insertions or deletion together. Why you want to do that, by the way? Why you want to batch insertion and deletion together? Huh?
Because essentially those sales would they eventually put together. So
Well, together is a good keyword. Essentially, by group them together, you can kind of look at their ordering to increase locality. So So suppose I do insertion like this. I do insertion of 1, then I do insertion of 10,000, then I do insertion of 2, I do insertion of 10,005. If you do this one by one, what do you end up doing? Retrieve this part of tree, update, retrieve this part of tree, update, come back, retrieve this part of tree, and so on and so forth. Imagine you have some process going on at the same time, you end up with random IO all the time. If you kind of shuffle it a little bit, so you do this together, and then you do this together, well, suddenly buffer utilization rate is much higher. Because you have locality. Most likely 1 and 2 is in the same page. You follow me? But that's only one benefit you get. What's the other benefit? If you have deletion coming in at the same time, well, if you order insertion and deletion, you reorder them a little bit, you can avoid a lot of split and merging. No? Okay? Alright, so that's, yeah.
As far as the index is concerned, I mean, inserts and deletes, even in bulk, I mean, you still have to look at them as being done individually, right? Like
well, but when you pin page, if you reorder them like this, most likely the page is already in the buffer.
So does
that increase the locality, that reduces the I/O, right?
So does the DBMS take care of ordering them before?
Does DBMS what?
Take care of ordering them before?
Oh,
because I mean, in most systems, like
it depends on which database management system you talk about, right? So
like Oracle usually,
yes,
they recommend that
in commercial level database, they will have something like this. But oftentimes this is something the DBA has to do. Because why? Because DBA has to tell the database, you know, what is the liveness demand of your database. If you say, okay, for any insertion deletion request coming in, it needs to be reflected immediately in my database. Then this batching operation doesn't work. Well, any attempt to try to batch them together or group them together will introduce delay in pushing this record back to the database, pushing this operation back to the database. And for mission critical operation, this might not be okay. If you transfer dollars from one bank to another bank, forget about efficiency. I get $100 off here. I want to see $100 on another account immediately. Don't tell me you try to optimize the bank. I don't care. That's your problem. But let's say you try to register the database class. Somebody else try to register some class. You know, I don't see my registration status reflected immediately. Who cares? Right? Do you care? At the end of the day, as long as the system tells you you are registered, even though it's not reflecting, but we will take care of that just 2 seconds later. Do you really care?
So, I mean, if that matter, if there's like contention in class, if there's one spot left, then you try to register 2 people at once?
Huh?
So,
you have a cap requirement.
Yeah.
Well, the thing is, remember, when I reorder this is in buffer, I can still maintain that cap constraint, but it's not permanently reflect on database yet. That's what I'm saying. It doesn't mean you are changing your business logic. You are not. It's just that those changes may only be in the buffer, but not push back to the disk immediately. That's what I'm saying.
So you basically you tweak when you write to the disk.
Not the
when you
DBA
flush
will
the
configure the database in a way such that whether you want to have this type of optimization going on or not.
Oh,
Okay. All right. So now let's look at hash index. Some further detail. Okay, hashing and hash index. So we talk about hash index briefly, right? But the hash index we introduce is static hashing, meaning that you have a number of buckets initially you allocate for, you have a hash function, then search key value coming in, you allocate the entry to the corresponding bucket. When a bucket is full, you just allocate overflow pages to that bucket. And the problem with that is eventually you will end up with some bucket that has a really long overflow list of pages. And then the efficiency of your hash index basically diminishes. Right? You don't get any benefit of using this hash index anymore if you have a really long list of overflow pages for any given bucket. Right? So the point of this discussion is to address this very problem, which is to dynamically reorganize this bucket within a hash index so that we can get rid of really long overflow lists. Okay, so that's the point. And in particular, we're going to talk about two famous constructions in the literature. One is linear hashing, the other is extendable hashing. So this is not only useful for database systems. In a lot of interviews nowadays, if you interview with Google and so on and so forth, very likely they will ask you about hashing, because hashing is such a fundamental tool that you use in many, many different constructions. So it will be useful to know this even if you are not trying to do database related stuff. Okay? So let's look at this. So this is, I don't have to repeat myself, because I've seen this before, right? So this is a static hashing. The problem is you're going to have, you may end up with a really long overflow chain like this. So static hashing, we talk about this. So let's look at extendable hashing first. Then we talk about linear hashing. So you can look at this table here, which I'm going to skip. I will go directly to an example with a picture, because picture words in 1,000 words. It's easier for you to understand. You can read the text description itself often. Right? So in extendable hashing, the basic idea is as follows. I'm going to maintain a directory. Okay, a directory. You can think about this directory as meta bucket, super bucket for my hash index structure, super bucket. Then for each directory, I'm going to have a pointer to a local bucket. This is what I call a local bucket. Okay? And the directory has a key parameter, a very important parameter called the depth, which we call this value as global depth. In this case, it's 2, which means each bucket here is recognized by using only 2 bits. So 00011, that's all. And what happens here? Each local bucket will have a value similar to that, what we call local depth. Local depth must be less than or equal to the global depth. In other words, the value here cannot be greater than this value here. It can be equal to or less than it. So in this case, local depth is 2. In this case, local depth is 1. In this case, local depth is 2. So what's the significance of local depth? Well, local depth tells you how many bits you are using to distinguish entries coming to this bucket. In other words, for entries in this bucket, I'm looking at 2 bits to distinguish them. In particular, you always look at the least significant bit. Okay? Least significant bit. In other words, you are looking at the two least significant bits here and the least significant bit here, because the depth is 1. To distinguish this interest. Furthermore, the bits I'm talking about is not from the entry themselves. Rather, it is from the hashed value of those entries. From the hashed value of those entries. In other words, let's look at this example. If I hash a record R is basically a search key value R. And the output is 5. Suppose I hash it, the output is 5. And the binary representation of 5 is what? Is 101. So since global depth is 2, I should look at only the last 2 bits, which means I should ignore the 1 from the most significant bit 1. Look at only the 2 lower bits, which is 0, 1, which means this record R, this data entry R should go to which bucket? 0, 1, which is this bucket right here. Let's look at another example. If my search key value R, I hash it, the value is 7. The binary representation is 111, and the global depth now is 2. I should look at the 2 least significant bits, which is 1, 1, which means this R should go to this global bucket here, and then this local bucket here. So both 5 and 7 end up here. However, a critical observation is 5 and 7 comes from different paths. One comes from here, one comes from here. By the way, for illustration purpose, the values here are not the search key value, rather the hash value of those search key values. Okay, you follow me? Not the actual search key value, but the hashed value of those search key values. In practice, of course, you store the actual search key value, not the hash value of it. But for illustration, to make sure you understand what's going on, I show the hash value of it. Okay? You may wonder, 5 and 7, the last 2 bits is different. One is 0, 1, one is 1, 1. Why they still end up in the same bucket? That's because the local depth of this bucket is 1, which means I distinguish this entry only by looking at the last 1 bit. As long as your last 1 bit is the same, they will be in this bucket together. All of this, if you check, the last 1 bit is what? Is 1. But their last 2 bits could be different. Could be either 0, 1 or 1, 1. What about this bucket up here? Well, for those guys, since my local depth is 2, so I will distinguish them by looking at last 2 bits. Which means the last 2 bits of them all of them must be 0, 0. You cannot have some 0, 0 or some is 1, 0. That cannot be the case because the local depth is 2. You do look at the last 2 bits. Now, so far so good, right? So far this is still a static data structure. What do I mean by that? If I insert another value with last 2 bits either 0, 1 or 1, 1, which means last bit is 1, I will come here. Suppose my max capacity is 4, I don't have space. So what do? I have to introduce an overflow bucket and connect it. That's exactly the problem we try to address, right? So in extendable hashing, here comes the critical part, which is extendable hashing doesn't allow overflow bucket to exist at all. As soon as you have an overflow bucket, you will split that bucket. Okay? And that's when you will increase the local depths, and when necessary, you also need to increase the global depths.
But in this case, we need to restructure all the data.
I will show examples, so hold on to your question. Right? I will address your questions. Okay, so let's look at it. So this is the description of it. I will skip this again. I will just show an example of it. Okay, let me insert 21, then 19, then 15. So if you insert 21, By the way, again, these are the hash values. You already applied the hash on the search key values. Right? These are not the search key values of the entries you try to insert. Rather, these are the hash value of those search key values. So if you try to insert 21, what happens? Well, the global depth is 2, which means you should only look at the last 2 bits, which is 0, 1. Come here. Do you have space? No, you do not. You do not have space for this bucket. What do? You have to split. Whenever you split, you increase the local depth by 1, and you check if the new local depth value is larger than the global depth value. If it's not, that's an easier case to deal with. Because if the local depth is less than the global depth, you know what? You know you have some directory entries from this meta bucket to cater for this split. Otherwise, you have to increase the size of this directory entry should the local depth value be greater than the global depth value. In this case, it is not, which is good news for us. So we will just split this, increase the local depth, which means by increasing the local depth, you change one subtle thing, which is how many bits you use to distinguish the entries in this bucket. Before this, you look at the last 1 bit, all of them are 1, which is okay. Now, you look at the last 2 bits, they're different. They're different now. Right? Why? Some of them are 0, 1, some of them are 1, 1, which means they should go to a different bucket now. So you allocate a new bucket. The 1, 1 come here. 0, 1, 21 and 0, 1 goes there. You update the meta bucket, the directories. That's it. Because the other one, 1, 5, and 13, you check, all of them have last 2 bits equal to 0, 1. That's why they stay behind in that whole bucket. Now, if I insert another one, let's say I insert 19, what happens? The last 2 bits of 19 is what? It's 1, 1. So where should I go? There. 15? So here. Okay? Now, continue this example, I'm gonna show you a case where a split on a local bucket will result in a change to the global direction. That happens when your local depth value become larger than the global depth values. And then you don't have this pointer to kind of leverage on, right? You don't have spare pointer to leverage on, essentially. So let's show an example of that. So I basically move the same example to this slide. I continue from here. So let's say I insert 20. The hash value of a search key is 20. 20 is what in value? So 16 is 0, 0, right? 17 is 0, 1. 18 is 1, 0. 1, 1, then 1, 0, right? Huh? No, 0, 1, 1, 0, 1, 1, and 0, 1, right? 0, 1. 20 is 0, 1. So 20 is 0, 1.
This is divisible by 4.
Huh?
This is divisible by 4, so it should be 0. Are you talking about last 2 bits?
I'm talking about last 2 bits. I'm talking about last 2 bits.
0, 0.
16,
This is
17, 18.
divisible by 4.
21 is 0 and then 20 is
So it's 0, 0, yes. Okay, there we go. Okay, good. Okay. Yes, 1, 1 plus 1 is 0, 0. Okay. So 20 is 0, 0. So you go to the top bucket over there, and you increase the local depth, become 3, which means you have to distinguish these guys by looking at last 3 bits now instead of last 2 bits. So the one stay on top should be 0, 0, 0. The one go to the other bucket should be 1, 0, 0. Because we're in binary work, right? If you look at one more bit, you kind of do a binary partition, essentially. Initially, all of them are 0, 0. Now they are 0, 0, 0, and 1, 0, 0. Right? We're in binary case. So all the 0, 0, 0s stay behind, which is 32 and 16. All the 1, 0, 0 will go to another bucket. However, now you check your local depth against global depth, you realize your local depth is bigger than the global depth. What you have to do? You have to change the direction entry of the global depth, which increase that to 3. However, this comes the interesting part. By increasing this to 3, what happens? You effectively double the number of direction entries. Why? Again, we're in binary world, right? Increasing one more bit means double the size of your output. So from 4 entries, you go to 8 entries. But the interesting part is, not all of this entry will point to an actual bucket. Some of them will point to the same bucket. Why? Because those buckets, the local depth is 1 bit less than the global direction. You are, even though your global direction look at 3 bits, but my local depth only look at 2 bits. That means 111 and 011 will end up in the same bucket if the local depth is 2 for those two. In fact, all of them will have local depth of 2 except the one you have just split. That's what you end up with.
So
Yes?
does it matter what the hash function is? I mean,
Does it matter what the hash function is?
I mean, it could be
Well, the hash function you use will be, you can use the same hash function we talked about before, which give you pairwise independence. And you look at this output in binary representation, and look at the last 2 bits of it. Of course, the not a big prime number p here, and then you look at the output, and you look at the last 1 bit, last 2 bit, last 3 bits, depending on your global depth, then local depth. That's all.
but then you're restricted to P entries, right?
Huh?
You're restricted to P entries, aren't you? Because I mean, you'll always
Not
hash-
p entries, log p. Let me see. You look at the binary representation. Log
Yeah,
p.
it's always
bits.
going to be
Log p bits. Oh yes, p entries. Yes.
P
Log
entries. P
p.
entries is the hash that domain will be.
Well, you can, if you choose a prime, let's say you are using 64-bit machine. P is 64 bits.
Oh, okay.
2 to the power 64. I mean, if you have a, if that large kind of handle, I don't know what can handle. And the idea is you're not using all 64 bits initially. You start with 1 bit, 2 bits, you gradually grow. That's the nice part about this. You grow this on demand when needed.
But of course, I mean, the limit is going to be P. The
The-
limit will be P.
The limit will be P, of course. But to the 64 bits, I mean, how many particles in this universe? Do people know? How many particles? Particle, like
This is about 10 to the 60,
10 to the 60,
or 10 to the 90.
10 to the 9 particles. Which is, if you convert this to binary, which is about 2 to the power of something. Okay, you cannot store the universe. Big news. Okay. All right. Yes.
So in this example, are we saying that that P is no longer the bucket size or the number of buckets?
Well, what he's saying is the limit. If you grow this to the very end, how many bits you can use? Of course, log 2p bits.
Well,
Because in mod p, right, the value is represented in log 2p bits.
what I mean is that
In this example, of course, is 3 bits, right?
well, what I mean is because we still have the 15, 7, 19, for instance, they all stay in the same bucket. So that means they all hash to, or the hashes are 15, 7, 19. But now that we've increased our buckets by 1 bit, so we essentially doubled that.
You double the direction entry, but you are not doubling the number of local buckets you have. You only double the direction entry, right? Which is different than doubling the. You do not make a copy of this. You simply make 2 pointer point to the same local bucket.
But because we split, there is one more, right? So it's no longer.
There one more direction entry. Yes.
One more of the buckets too, because we've split.
One more bucket where? Like local. Yes, there's one more bucket here. Yes, of course. Yes.
So that means our bucket size has changed. But
You bucket, the number of buckets grows, but not doubling. That's the key point. You double the direction entry, but not the number of buckets every time you split.
well, what I mean is just because the hash we were using in like the last project was depending on the buckets, the number of buckets, and so if our number of buckets is not.
Well, here we are not mod the number of buckets. We are simply mod a big prime number p. Then we look at the bits.
So they're not.
There are no fixed buckets per se in this case. It's different, right? So it's a different design of hash function. Okay. Now, are we happy with this? Are we happy with this? Is this good enough? Is this good enough? Well, depending on how you look at this, right? On one hand, you do not have any overflow pages anymore, which is fantastic from a query point of view. Why? Because I guarantee you any equality search is constant I/O. You hash one bucket, you find what you want. Because there's no overflow chain, right? So query must be really efficient. But what's the downside? Well, if you know that's what the system is doing, you can, as an adversary, right? Suppose you are Google and Microsoft. And I know you're using extendable hashing to index your HTML pages. What I'm gonna do, I'm gonna hire a bunch of people, I pay them $10 a day. Like, you create this hash page, this HTML page with this content in it. Such that the hash of them, you see the pattern, right? What happens?
It's really big for the
Here's
task.
some-
They are
here's some really high-
they have so many common bits at the lower orders. You can only distinguish them all the way to some really high order bits. Do you see what I'm saying? Meaning that they look really alike. They differ by just a little bit. You have to use so many bits to distinguish them. That's essentially from an information theory point of view what you're saying, right? So how many bits I need to tell the difference of these two? Well, just a little bit. How many bits I need to tell the difference between this and this? A lot. So what you do is you create a lot of pages like this, just differ a little bit, all like, and then the lower order bits are all the same. You need to use that many bits in order to tell a difference. To tell a difference between Feifei and this thing, you probably need just one bit, which is human or not. Now, can you distinguish this by one bit, human or not? Well, no. Animal or not? No. 2 bits. Doesn't help. Keep going. Right? You see what I'm saying? So that's the point. So if you have a lot of entries that are so similar, so hard to distinguish, which means you have to go to a really high order space to distinguish them, which means you have to use so many bits. So lower order bits are going to be the same. So you have a lot of those entries. What happens? Well, yes, you do not have overflow chain, which is nice. But what happens is the disparity between your global depth and the local depth of most of your buckets gonna be so big. Most of your buckets have a local depth of 2, but your global depth might already be 64 for the stream case. 64 is huge. Because we're talking about 64 bits. Okay? That's 2 to the power 64 entries for your directory. At some point, the overhead for storing these directory entries will be what? Will outweigh the benefit you get by reading off overflow lists. One thing you need to pay close attention is not only you are doubling the number of directory entries each time you increase the global depth, you are also increasing the amount of space or number of bits needed for each bucket. Each directory entry after the doubling operation. So actually grow more than doubling space-wise. Initially you have numbers only 2 bits, and eventually you have numbers of 2 to 6. So, same thing. If you represent 10 numbers of 64 bits each and 10 numbers of 2 bits each, yes, you have 10 numbers in each case, but the cost is dramatically different, right? That's my point. Right? All right, so that's the problem with extendable hashing. And there's also the deletion you can do for extendable hashing, which is essentially the reverse of what I have shown you, which I'm gonna skip. It's not that hard. when you delete entry from a bucket such that the local bucket become empty, what happens? You decrement the local depth by 1. When you have 2 local depths that share the same common bits with 1 bit less than the global depth, you can what? You can merge them. With that, I stop right here. I will talk about another construction on Tuesday. I was trying to do some demo of my system. I will do that on Tuesday as well. We will talk about another hashing construction on Tuesday, which is linear hashing, to address this very shortcoming of extendable hashing. Okay. All right. See you guys.